Okay. Hello, everyone. Welcome to today's webinar on harnessing control techniques for seamless multi-agent coordination. My name is Rajeev Voleti, and I'm a software engineer specializing in modeling and simulation. And I'm excited to share with you how we can use JuliaSim for multi-agent coordination, particularly in this case, in the context of quadrotors and ground vehicles. So here's the agenda for today's webinar. We'll start with an overview of JuliaSim and its capabilities, especially in control and simulation. Then we'll move on to discuss quadrotor trajectory tracking, followed by cooperative coordinated rendezvous techniques. I'll also demonstrate a practical code example of the quadrotor landing capture using JuliaSim, aerial vehicles, and InfiniteOpt. Finally, we'll conclude by discussing future directions of our work. Let's begin with JuliaSim. JuliaSim is a powerful tool for modeling and simulating complex systems. The idea is to have a single environment that can address most or all of the engineering workflows. It's built using the Julia programming language and the open source SciML ecosystem, which gives us both the speed and high-level syntax similar to Modelica. In particular, AerialVehicles.jl is built upon Modeling Toolkit, a declarative acausal modeling language similar to Modelica. JuliaSim provides a series of pre-built libraries such as Modeling Toolkit standard library, which is similar in spirit to the Modelica standard library, HVAC, battery, and multibody. Additionally, JuliaSim offers tools for engineering workflows such as model calibration, control, including PID, MPC, and support for nonlinear MPC as well, and model acceleration by constructing neural surrogates. As shown here, we use Modeling Toolkit, which allows us to define models in a modular component-wise fashion, similar to Modelica. So this capability forms the backbone of our ability to model dynamic systems like quadrotors. So specifically today, we will look at designing systems in ModelingToolkit.jl and generating trajectories and control inputs for the quadrotor using JuliaSimControl. Before we dive into the method itself, it's important to note that it takes full advantage of certain key features in the Julia programming language, particularly automatic differentiation. The first step in the process was setting up the models for both the quadrotor and the ground vehicle using Modeling Toolkit. One key point to emphasize is that Modeling Toolkit shares many similarities with Modelica in terms of syntax and semantics. For example, in an RLC circuit model, we can define a connector that behaves very similarly to those in Modelica. Additionally, Modeling Toolkit allows us to extend models, define parameters, write equations, and much more in a manner that feels very familiar to anyone with experience in Modelica. As you can see, both Modeling Toolkit and Modelica have a very similar approach when it comes to building models. To create a model, we first define the individual components, and then we connect them together using equations. On the left side, we have an example of how this is done in Modeling Toolkit. We begin by defining components such as resistor, capacitor, inductor, and a constant voltage source, and a ground. So once the components are specified, we write corresponding equations to connect these components. These connections represent the physical relationships in the circuit. On the right-hand side, you'll notice a Modelica example of the same model. The structure is quite similar. We define the same components and use the connect function to link them. This similarity in syntax and structure makes transitioning between Modelica and Modeling Toolkit quite intuitive, especially for those already familiar with Modelica. The main difference lies in the underlying language and some of the features unique to Julia, such as automatic differentiation, but the modeling workflow remains quite comparable. Modeling Toolkit is built on top of Julia, a fully featured programming language, which means we can seamlessly integrate the model creation with analysis scripts. For instance, as shown on the slide, after defining the model, we can also perform the analysis directly in Julia by scripting it. Here we use the mtk build macro to compile our RLC model, and then we set the initial conditions for the capacitor voltage and inductor current. Next, we define an ODE problem that uses the RLC model. along with the initial conditions, and we solve it over a given time span. Finally, the results can be visualized using Julia's plotting libraries, in this case, plotting the capacitor voltage and inductor over time. This highlights how easily you can switch between model creation and analysis and leverage Julia's extensive package ecosystem, including solvers and plotting libraries, without leaving the language. So now I'm going to start with an introduction to the quadrotor trajectory tracking problem. So we'll start by examining the design of the quadrotor model. The dynamics of the quadrotor are derived using a force balance approach on a rigid body. So importantly, the quadrotor is a differentially flat system, meaning it can be fully described by its flat outputs, which in this case are the position in space, x, y, and z, and the heading angle psi. To capture the complete state of the system, we use variables that include the position, velocity, rotation matrix, and the angular velocity. These variables describe the quadrotor's configuration and dynamics at any given time. So the model is defined within ModelingToolkit.jl, where we can describe the system dynamics and later apply control or estimation techniques. The quadrotor is a well-documented problem in control systems and serves as an excellent platform to demonstrate various applications such as controls, estimation, and optimization. So to follow the trajectories design, we use a nonlinear geometric controller. The idea behind this is similar to backstepping control for those who are familiar. So this involves designing desired dynamics for the quadrotor and then stepping back in the states to cancel nonlinearities and inversely find the control input required to affect the desired design dynamics. So the advantages of using geometric controllers is that it accounts for the nonlinearity of the system. The state decays to the desired value of the output exponentially, thereby ensuring precise tracking, which, as is evident from the graphic, is hard to do with just a linear PID controller. So with the geometric controller, we are able to execute complex and acrobatic maneuvers, such as stabilizing a falling quadrotor or having it track a tight spiral trajectory. So these type of maneuvers are achieved much more effectively and robustly than with just a standard linear PID control. So in the visualizations shown here, we see two examples of the quadrotor performing such maneuvers that demonstrate the geometric controller's superior handling of nonlinear dynamics. Whether it's stabilizing quickly from the free fall or tightly following a complex path, the geometric controller provides the necessary precision and agility. So this slide outlines the overall structure of a trajectory optimized quadrotor using a geometric controller. So the process starts with a series of waypoints and the corresponding time required to achieve these waypoints. So these waypoints are then fed into a trajectory optimizer, which synthesizes the desired output, which is a polynomial in time of the set of target states for the quadrotor to follow. The desired output is then passed to the geometric controller, which, along with the quadrotor state feedback, generates the appropriate control signal to ensure the quadrotor accurately tracks the desired trajectory. Both the control generation and trajectory optimization are implemented using JuliaSimControl, and the quadrotor model itself is part of AerialVehicles.jl, which is a library within JuliaSim. So in this visualization of the simulation, we see the quadrotor following a trajectory generated between 4 waypoints. So now that we've looked at the quadrotor trajectory tracking problem, we'll come to the cooperative control part of the problem. So in this case, we look at a non-homogeneous system of vehicles. By this, we mean that the dynamics of each of these vehicles are different from the other. We consider a quadrotor and two ground vehicles for same time or simultaneous rendezvous. The ground vehicle controllers are custom receding horizon controllers, and they each have either like the Dubin-Scar dynamics or a differential drive dynamics. While modeling for all the vehicles are done is in MTK, we use InfiniteOpt, which is an interface in JUMP, which is Julia for mathematical programming, and IPOpt to solve the optimal control problem generated by the custom controllers. So we make use of JuliaSimControl and InfiniteOpt with JUMP in our simulations, underscoring the flexibility of modeling toolkit models to be part of the same workflow with JuliaSimControl and something that's completely open source like InfiniteOpt. So the cooperation in this case is classified as objective-based consensus. So for further details on this approach, I would implore you to read the reference provided. But essentially what this means is that the cooperation of the state that is shared is set by the leader or the objective, which in our case is a quadrotor. We assume that it is physically possible for the ground vehicles to reach their rendezvous destination. The only shared state among the agents is their own time to go, or TGO. The quadrotor shares its time to go every second, and the ground vehicles use this to compute the optimal control for arrival. So the definition of our optimal control solution is obtained using the maximum principle. So for our application, we assume the cost to minimize is the control energy represented by L here, and TF is set to the time to go of the quadrotor when consensus is evaluated. The equivalent NLP to solve for the optimal control problem is well documented and given here. So the equivalence can be found in literature fairly evidently. So we leverage the structure of an nth degree collocating polynomial in states and control initially rolled out, and then we optimize the coefficients based on our cost. So in our framework, we compute the optimal controls and use a control trajectory for up to NC samples, at the end of which consensus is time to go is reevaluated. T here refers to the discretization time interval. We choose Gauss-Lobato routes for the collocation points for reasons that have to do with the boundary conditions that we pose. So as shown in the figure, using time to go, we estimate the number of time steps to consensus NT. This interval is further split to NC. So each horizon now has a set of scaled collocation points depending on the degree of the collocating polynomial. So our approach is pretty similar to an MPC, but not really, because MPC has a horizon, but in our case, we have an end objective in mind. And the custom receding horizon controller sort of adapts its approach based on the requirement that is in the moment. So if the time to go changes, the horizons change and the control computed completely changes, which is not the case in MPC. So once a mechanism to find the solution to the NLP has been obtained, the framework of consensus and convergence is piecewise optimal. Although with the caveat that the time to go consensus must occur before considerations of optimality. And this would come into picture if you have a large network of ground vehicles that don't necessarily are not completely in communication with each other, or they have a custom network that's not a complete graph. So using Bellman's optimality principle, which states that an optimal policy possesses the characteristic that irrespective of the initial state and decision, the subsequent decisions must comprise an optimal policy concerning the state resulting from the first decision. So it is evident that after consensus and time to go is achieved, the control generated will lead to an optimal solution. So for our equivalent NLP, assuring second order optimality in order to conform to Bellman's principle would imply the generation of a Hessian of the order of the degree of the collocating polynomial times the number of discretization intervals by the number of states of the system. And then we raise an error flag if the Hessian is non-positive. So in this simulation, we'll see the rendezvous of two ground vehicles with varying dynamics, with a quadrotor utilizing a polynomial trajectory following a geometric controller. The quadrotor hits 3 waypoints before the landing cooperation is triggered. At this point, the ground vehicles receive time to go information from the quadrotor every second and achieve rendezvous with their target. The final position of the vehicles can also be tweaked to be coordinated with the capture of the quadrotor. The rendezvous is optimal, non-homogeneous, secure due to the fact that the positions and velocities of the quadrotor or ground vehicles cannot be ascertained based on the time to go, and autonomous. So now I'm going to share my screen and show you some of the code that went into getting the simulation up and running. Okay, is my screen visible?
Yeah, it's visible, yes.
Okay, so we're going to start off by calling a bunch of packages, JuliaSimControl to generate the to generate the trajectory, to generate the control for the quadrotor, and aerial vehicles for the models of the ground vehicles and the quadrotor. OSQP is what is being used to generate the trajectory in the polynomial trajectory optimization process. Yeah, a modeling toolkit for obvious reasons that's what we're using to model our system. Control systems base, GL Maki for the visualizations, rotations in order to sort of have the output to be able to visualize things, data interpolations to match the rate at which simulations are being generated in the quadrotor as well to the ground vehicle. So the arrays are not of different sizes. So in this case, I've broken up the problem into two, so it's much easier to follow. We start off by just doing the quadrotor simulation, which is we have a bunch of time segments. So X is the initial waypoint. And then we have, these are the waypoints that the quadrotor is going to hit, which is the X, Y, Z. And then that's the orientation. So we're just going to have it hit the points at the same orientation. So we start off at 0, 0, minus 10, which is the origin. And then vel is the initial velocity. So if you want the quadrotor to sort of start with a non-zero initial velocity, you can do that as well. And then we use this function to generate the optimal coefficients of the polynomial. Using this, we generate our trajectory in time. And then we start by initializing the quadrotor model from aerial vehicles. We define our control gains. We pass these gains into the geometric controller construction. And then this is to find a static relationship between the MTK model and the inputs, so we can simulate the controller that we've just generated. And this states that the modeling toolkit model is complete, that we don't want to add anything or sort of change any parameter, that we are done modifying the quadrotor model, and that's what we will use to simulate it. So we start by specifying the initial conditions. We use this function in aerial vehicles to build a vector of the initial conditions. And it just running the quadrotor is as simple as setting the final time to be the sum of the array of times. And we call one function to generate the state, which is run quadrotor sim. After running this, we extract the states. All of this is essentially just extracting the states in order to animate them or visualize them. So now we move on to the cooperative simulation. Similarly, we have a bunch of packages that we call. We define D to mean the differential. We set the final positions of the quadrotor beforehand. They will not be sharing this information. The only thing that they will share is the time to go. Same for DD, here refers to the differential drive ground vehicle. So we initialize this with a large number just so we don't run into array size issues. And we initially roll out a trajectory for just an assumed time to go value. This initializes a trajectory for the Dubin's car ground vehicle. This does it for the differential drive. Now, we define two separate models in Modeling Toolkit. We call our Dubin's car, and we use this sample data function from the Modeling Toolkit standard library. What this does is, as you progress through, you can feed information to this sample data block at a rate of dt. So we're sort of leveraging this. We can simulate this straight off the bat. But the reason in doing this is because a lot of the feature or a lot of the importance of this whole method is the fact that it can adapt to things in real time. Is that if something changes in between or at a certain time, if the quadrotor decides, no, I'm not going to land now, the whole system updates in real time based on that specific reaction. So it's a time-dependent process. And because of that, I wanted to set up the simulation so it steps through in time so we can observe that behavior. We do something very similar to the differential drive. We specify the control inputs, the U left and the U right, the velocity of the left vehicle and the right vehicle, the right wheel and the left wheel. And specifying the connections just as easy as saying connect. So this is the control input. We are just connecting that to the buffer. And then the right buffer is connected to the right input. So this builds essentially our buffer-enabled Dubin's car and differential drive. So I'm going to start by giving it a buffer of just ones. So you will see that the car, the ground vehicles start off with an initial control that's not optimal. It's just going straight. It has no sense of when the optimization process starts. 1 second into the landing start, I did that specifically so it doesn't seem like I just ran an optimal control problem and it's just going smoothly and there's like no sort of reactivity or time dependence that is being taken into factor. So we push the initial control input to be just a unit control input. We define the ODE problem for both. And then we set up the integrator for both the ground vehicles. So this would enable us to step through the model from 0 to say anytime. And then we begin by defining both their time to goes. This is a specification that says that time to go consensus is evaluated every delta t seconds. I can tweak this parameter based on whatever I'm trying to achieve. It's only saying start this after 6 seconds, because if you recall, it's not going to start landing until it hits the 3 waypoints. It's going to initiate its landing maneuver after the 3rd waypoint is hit. And this is just a straightforward way of doing it. I can also include a condition or a flag that says initiate landing. And then when it does that, this whole loop can run. But for now, it's structured this way just for simplicity. So we start by pushing our initial control that we have, the unit control inputs, and then we generate the optimal control inputs using this function. So optimizer diff drive, if I go into the ground vehicles model library, you can see that it is set up, yes, or Dubinskar, it's set up in InfiniteOpt. And so we use InfiniteOpt locally in each of these ground vehicles for a distributed simulation. We are not using JuliaSimControl here. InfiniteOpt is completely open source. Modeling Toolkit is, again, completely open source. And this is just a way that I'm using to demonstrate the power of the Julia ecosystem, in that you can take all of these packages and sort of work with them in a single workflow. So we define the objective here to minimize the control effort. We define constraints, all of those good stuff, and it runs the optimizer. So when we go back, every time we call this, which happens every 1 second, it runs the optimizer to generate the controls and then pushes the generated controls to the buffer. Now we have what happens in between time to go consensus intervals. It just, because this is a generated array for up to the time to go of landing, you can just locally push the generated trajectory that you have obtained, and this will reset every 1 second. And so at the end, since the control generated will be 1 less than the state vector, I push it 1 final time. And we also have a notion of terminal convergence, which is, it doesn't make sense to share a lot of information as you're getting really close to the docking of the model. So it enters a terminal state in the last 2 seconds. And when it does that, it stops sharing all information. It relies on the information it has about what the optimal way to approach the quad is. And it does so based on that last bit of knowledge. And this helps sort of avoid any issues you have of infinite convergence, or as the quadrotor is arbitrarily getting close to the endpoint, they might think that the time to go is very high. So in order to avoid those situations, we have a terminal approach that takes this into account. And then the last part is just extracting trajectories. We obtain the solution from the integrator that we've stepped through, and we extract the time, we extract the states, and then finally we animate them. It's not necessary to extract the states. I just did that because it's kind of cool to look at and visualize instead of looking at some boring plot. So I use GL Maki to do this. And when I run my script, yes. So it hits 1, it hits 2, it hits 3. When it hits 3, it starts with like a certain initial input, but the approach is smooth. And another thing to highlight here is the reason why the quadrotor looks this smooth is the fact that it's a minimum snap polynomial that's generated. And minimum snap means the trajectories are going to be really smooth. The snap is 1 over jerk, which is 1 over acceleration. So what the polynomial generation does is it minimizes the second derivative of the acceleration, which makes the approach the hitting of waypoints, the tracking of the trajectories extremely smooth. And because we have the means to do this, cooperative control should sort of evolve in a direction that leverages these features. And the fact that we can at any point calculate the time to go that these ground vehicles require. And in this case, I would also like to highlight the fact that there was no gain tuning involved in the ground vehicles. And the approach sort of leverages the exchange in information of time to go that is very readily available using the trajectory tracking mechanism. So yeah, with that, let me go back to the presentation now. Is my screen visible?
Yep, it's visible, yes.
Okay. So it is in its nascent stages. There are a lot of things we are going to do about this in the future. A small sneak preview is the fact that we actually want a component-based model of the quadrotor and not necessarily just an equation-based model. So for that, we are going to leverage JuliaSimMultibody.jl, which is now available to view publicly, although it is proprietary and licensed. But please check this out. It's a really cool feature. The advantage of having a component-based model is that it's acausal, and the fact that it's literally a plug-and-play model where you don't have to worry about a lot of the nuances that you generally worry about in terms of fidelity and geometry and stuff like that in the flat equation-based model. So this is something that can already be worked on. Is we have a component-based 6 degree of freedom multi-body model of the quadrotor with a cable suspended payload. I know that is a lot of interest to a lot of folks. So this would be the immediate direction we'd be heading in. And starkly, we have some wind force models in aerial vehicles that work, but now they can work even better because we have discrete time modeling capabilities. So you can now, all you have to do is just drag and drop the wind force model into your component, into your simulation, and then just plug the wind forces into your quadrotor and then run it. And then it would just stimulate wind. So that is also something very close to being done, considering the new discrete time capabilities we have in Modeling Toolkit. So we also want to support a wider range of control methods. I did the geometric controller because I found that it was interesting. We have PID available, but it would also be cool to have some nonlinear MPC or a wider range of control methods. Now, we've talked about something pretty crucial to the working of cooperative system, which is network communication. It's not always going to be feasible to have two or like 10 or 15 ground vehicles in constant communication with each other. So we want to be able to sort of model the network communication between the two, where say ground vehicle 1 only talks to ground vehicle 2 and 3, and ground vehicle 5 only talks to ground vehicle 3. So in order to model that, it's going to need a little bit more of an involved approach, but that is also something that is in the works to support custom network communication for the models that you have defined in Modeling Toolkit. Or if you want to initialize a model in aerial vehicles, there should also be an option that specifies the shared communication between the vehicles. And another thing to make that happen would be the addition of n vehicle nodes to the system with the above specified network communication. So you should be able to say, I want 5 ground vehicles with this connectivity. And when you say that, you shouldn't have to sit there and struggle through with the adjacency matrices or setting up the communication exactly like how you want it. We should be able to do that on our end. So it should just be as easy as initialize 5 ground vehicles with, say, like a connected communication, like a star connectivity or like a leader follower or something like that. So these are things that we are actively working on right now. And yeah, that's all I have.
Thank you, Rajeev.
Thank you so much for attending, guys.
Yeah, thank you. And in case you have any questions, you can type it in, or you can share it with us, and we'll answer them in order we receive it. So you can type it in the Q&A section, and we'll pick it from there. Rajeev, let's wait for a couple of minutes and see if there are any questions.
Yes, sure.
Yes, the recording will be available to all the attendees. We will email the link to you. Okay, I see no questions coming in, so maybe we can call it a day. Thank you everyone for attending this webinar. As mentioned, we will share the record version of this webinar through an email, and you can attend our future webinars. You can go to our website and into the event section to see all the upcoming webinars, and we look forward to seeing you there as well. Thank you, Rajeev, and thank you everyone.
Thank you, guys.